So far we've considered only the binary classification case when there are exactly two classes. Obviously this is a bit limiting for general applications. We may often want to choose between multiple different classes of thing. One way we might choose to address this problem, given that we already have a functioning binary classifier, is to use multiple such classifiers with different combinations of the classes and figure out which one wins out. One popular way of doing this is the one versus rest approach. In this case, you train up a separate binary classifier for each of your classes, classifying that single class against all of the samples of all the other classes. This gives you as many classifiers as there are classes, and you just choose the one that has the highest prediction score. An alternative, but more expensive approach is known as one versus one. In this case, you build pairwise classifiers for all the different combinations of pairs of classes. You run all of these individual pairwise classifiers. They will be of the order of the square of the number of classes of these classifiers. Then you take a vote across all of these possible classifiers of which class gets chosen most often. However, let's assume that we don't want to just use a bunch of binary classifiers, and we want to have a dedicated classifier that is able to categorize things into more than two different classes. If we consider this question in similar probabilistic terms to those we took with logistic regression, then we need to have a distribution to assign to them which has multiple possible outcomes. The multi-class equivalent of the Bernoulli distribution is the categorical distribution. In this case, all of the possible outcomes have a different probability set for them. All of those probabilities must, of course, add up to 1. In the categorical distribution, we're assuming that every draw from the distribution is independent. When we were predicting binary outcomes, we only needed to generate a single probability value. Because there were two outcomes and probabilities have to add up to 1, there's only a single degree of freedom there. The probability of a positive class determines the probability of a negative class. For more than two classes, this is no longer the case. We need to have multiple outputs. That is to say, we will have a vector of predictions rather than just a scalar y. In principle, this vector only needs to have the number of classes minus 1 elements, because the final probability will be determined by the fact that they all have to add up to 1. In practice, we always use as many elements as there are classes because we want to avoid scaling issues. As the model outputs are vectors, we will also need the ground truth values to be represented in the same way. Since the true value can only be a single thing, this will be a one-hot vector of the kind we discussed last week. Just as with logistic regression, we would like to be able to take the continuous and unbounded outputs from our linear model and use that to specify a probability. To do that, we need to apply some kind of squashing function that compresses the range. In the multi-class case, the equivalent of the logistic function, or the sigmoid function, is known as the softmax function, and it looks like this. This function applies exponentiation to all of the outputs from the model, and in doing so, it amplifies the differences between the different predictions. The function is normalized by the sum of all of these exponentiated values, and that ensures that the outputs all add up to 1. One thing to note about this function is that, unlike the sigmoid function, this is a vector function of vector inputs. It doesn't apply element-wise, it applies across the entire vector. As a result, instead of being able to restrict ourselves to a single gradient vector, we actually have to deal with, at least in theory, the full Jacobian matrix. That matrix looks like this. It can also be expressed element-wise with this expression. However, the good news is that we very rarely have to use this in full, because the softmax squashing is commonly used in combination with a cross-entropy loss. And when you combine those two, there are all zeros, and all of the off-axis elements of the Jacobian disappear, and we don't have to deal with them. One useful piece of terminology for the outputs of the model that go into the softmax function is that they are called logits. This can be interpreted as the model's estimation of the log odds that the sample belongs to each of the classes. The advantage of the logits is that they are not restricted in terms of scale. They don't have to add up to 1. This same term, logits, is sometimes used for the inputs to the sigmoid function in logistic regression. That is to say, the unsquashed linear model outputs. As with logistic regression, we're going to use a cross-entropy loss to evaluate our model predictions. For the logistic regression case, we used a special case of the cross-entropy for binary outcomes, which enumerated both outcomes in the expression explicitly. But the cross-entropy itself is equally defined for any number of outputs, and we can construct a general categorical cross-entropy that looks like this. I'm not going to go through the full derivation here, but the gradient of the categorical cross-entropy is pretty simple to derive, and it looks like this. Remember that the ground truth value y is a one-hot vector, so almost all of the entries in this gradient are 0. We can combine this cross-entropy gradient with our softmax Jacobian using the chain rule, and the result looks like this. Importantly, almost all of the elements in the Jacobian have been eliminated, and we get back to just being able to use a single gradient vector. If we further combine this with the output gradients from our linear model, again using the chain rule, we get an overall gradient that looks like this for a single sample, and if we aggregate that across the entire training set, then it will look like this. This gradient expression should actually look kind of familiar. It's really very similar to the one for logistic regression. The key differences are that because there are multiple outputs, the W's and Y's are now matrices rather than vectors. The other difference, which is not obvious in this expression, but which is wrapped up in the estimation of y hat, is that we use the softmax function instead of the sigmoid function. As with logistic regression, there is no closed form solution for this, but again, it can be solved by gradient descent methods or second order methods in the same way. This whole process is known as multinomial logistic regression or softmax regression. But actually, in practice, it's often not really distinguished at all. For example, in scikit-learn, it is just the default implementation for logistic regression when applied to a multi-class problem. The combination used in this case of a categorical cross-entropy loss and a softmax squashing function is also used very widely as the final stage of many other kinds of classification models, in particular of deep neural network classifiers. The softmax squashing function allows the rest of the model to focus on relatively scoring the different options without having to worry about any absolute scale constraints. So the model can use whatever relative ranking and scale it happens to learn.